This is now the problem-solving part of the lecture. So first question from second chapter in the textbook. I'll just read them out. Which of the following sets is well defined? Now the set of prime numbers, is that a well-defined set? Is it clear which integers belong to that set or not? So what is a prime number? It's an integer such that no other integers can divide it except the integer itself and 1. So that seems a pretty clear specification, so I'd say that the set of prime numbers is well defined. Okay? How about this? People in the world whose birthday is on the 1st of April. That seems to me fuzzier. What about the international dateline problem? You have to be very clear. You need some lawyers to specify that one clearly for it to be a legitimate set. How about the set of one element where that one integer is the thousandth in the thousandth decimal place of the decimal expansion of pi? Well, it may be difficult to calculate, but I guess that it's clear, at least in principle. So I'd say that's a well-defined set. Okay, true or false? 0 belongs to Q. Is that true or false? Now what's Q? Remember Q? Oh, I rubbed it off, but Q is the set of all rational numbers. Now if you can remember, rational numbers were of the form a over b. A and b are integers, where b cannot be 0. So if a is 0, then this rational number is 0, so 0 can belong to Q, so I'd say that's true. Alright. Can 0 belong to Z star? Now I haven't put it here, but let's put it. So Z star. No. Now anything starred means you throw out the 0. So this is the set of non-zero reals. This is the set of complex numbers non-zero. So this would be the set of integers non-zero. So 0 cannot belong to that one. So the statement that 0 can belong to this is false. Okay? Can a set have just one element? Sure. You can have a set just like this. Yeah, just with the number 1 in it, or A, or whatever. You can have a one-element set. No problem. Explain why Z is a subset of Q. Why is Z a subset of Q? Now, Q, remember, is the set of all rational numbers, and rational numbers, they're of this form. So why is Z, the set of all integers, a subset of Q? Well, any number A belonging to Z, you can express that as A over 1, right? Same thing. And that belongs to Q by definition, because a rational number is of the form A over B. Well, B is just 1. So if A belongs to Z, then A over 1, which is A, belongs to Q. So any element belonging to Z, because of this reasoning, belongs to Q. Right? That's the definition of a subset. Therefore Z is a subset of Q. Right? I'll leave in the textbook this next problem, which is quite difficult. I'll leave that to the end. So I'll give you maybe one other. Alright, you have a set with n elements. Show that that set has 2 to the power n subsets. Okay, you got the problem? Have a set with n elements in it, and you create all possible subsets from that set. The number of possible subsets will be 2 to the power n. All right, well, here's how you could do it. Here's your set A, and let's say here are your n elements, and here's one possible subset. So we'll call it B. So B's a subset of A. Well, and you have to prove that there are 2 to the power n possible subsets of set A. So how do you do that? Well, here's one trick. Put all your elements on a line like this, and then look at the first one and then the second one and so on. And each time, as you're looking at each element, ask yourself, will I put that particular element or member of the set, will I put it into the subset or not? Now there's 2 ways you can do that. You can put it into the subset, or you don't put it into the subset, right? So you have 2 possibilities. And similarly for the second one. Now, for this first one, it can be in the subset or not. And for the second element, it also has 2 possibilities. It's in the subset or not, right? So let this be the position of where the first element. This is for the. So this element is either here or not, or is there or not there, depending on whether you put it into the subset or not. Okay. Now similarly for the second one. So just with those 2 elements, you now have 4 possibilities, right? So the first one, there or not there. The second one, there or not there. 4 possibilities. Now you can probably see the reasoning where I'm going now. So with the third one, also the third one is there or not there. So for the first 3 positions in the subset, there or not there, there or not there, there or not there. So that's 2 by 2 by 2. That's 8. So 2 to the power 3. Now you just continue this argument. So when there's 3, you have 2 to the 3 possibilities. That's 2 to the power 3 possible subsets. And if you have n, well, you'll have 2 to the n possible subsets. Okay, seem reasonable? All right, now let's do the hardest one in the exercise in the chapter, I suspect. And we'll take a bit of explanation. So I've written it out here because it's fairly detailed and a lot of steps and reasoning. Not easy. Okay. You're asked to prove that this statement here and this one. Let's call that statement P, and let's call this statement Q. So you're asked to prove that if the union of A and B is B, and the intersection of A and B is A, that those 2 statements, P and Q, are equivalent. Now, can you remember from the previous lecture on the nature of proof, the definition of equivalent? What if you have 2 statements and you're told that they are equivalent, what does that mean? So if you're scratching your head and you don't remember, I'll just tell you. 2 statements, by definition, are equivalent if you can prove one from the other, or the other from the one. So what we have to do here to prove that P and Q are equivalent, we have to from P derive Q, and from Q to derive P. We have to go both ways, right? So in other words, it's an if-if, IFF, an if and only if type proof. So it's any IFF. Go back to the previous lecture. Any IFF, if and only if proof, is 2 ways. To prove if and only if, you have to prove it in both directions. So that's what we have to do. So how to do that? Now it's not, you have to think of it. So let's do it in one direction. So A union B is B. That's P. So we'll call that P. And A intersection B is A. That's Q. Right. So But we will now try to do half of the problem. We'll try to prove if P, so if that's true, we have to prove that's true. Okay? So if P then Q. And that's only half the problem. So an equivalence problem you have to, that's an IFF problem. So you have to do it in both directions. So you have to prove it from left to right and you have to prove it from right to left. You have to go